All right, so just a reminder, we have quiz on Monday, end of our gas laws chapter, and sections 1 and 2 in chapter 5. So we'll be doing a lot of calorimetry today. So you'll have a calorimetry question on your quiz. Questions about that? Okay. So I came up with this little problem for the other class, which hadn't gotten to use the hand warmers yesterday. So we pulled out a hand warmer and I measured the temperature change. So the temperature went from, it was about 19.6, kind of cool in the classroom, and it went up to 55.5 degrees Celsius. And so we want to know how much heat that is. So we have to remember that we have a system and everything else in the universe is the surroundings. And so what is given off by the system, the chemical solidifying and giving off heat, that was absorbed by the surroundings. And so the surroundings is the water and the thermometer that was picking up that temperature change. Remember that Q is what we use for heat. So the system, opposite of the surroundings. And so in order to measure what's going on with chemicals, a lot of times if it's aqueous, you can just say, well, what's going on with the water, and assume that is the opposite for that chemical. So we said that since it was giving off heat, it should be exothermic for the heat pack, right? So it would be negative for the heat pack. So what would the sign be for the water? If they're opposite, positive. There we go. Okay. So we took 100 grams. I just kind of assumed that since, you know, if I weigh it, I'm going to be weighing both the chemicals and the water. So I approximated 100 grams at 4.184. And then our temperature change. Now it's important for a temperature change to do final minus initial. So our final temperature was 55 and our initial temperature was 19.6. Okay, and that's going to make it positive for the water, which is what we would expect. Okay, so if you have a calculator, go ahead and plug this in. A lot of times people will make mistakes with the temperature, both with flipping these or forgetting to close the parentheses. So it's a good idea to practice these calculations to make sure that you are plugging things in correctly. What do you guys? 15,020. So we would say it's something like 0.56, you said? Mm-hmm. This is what the calculator says. And then we would look at our significant figures. Now, we don't actually have 3 sig figs on our mass, but let's assume we did. So 3 sig figs here. Here we have 3 significant figures. And so we're going to round this 3 significant figures. And I'm going to actually write this over here so that the computer's not blocking it. When we have a change in the significant figures before the decimal, sometimes people get confused because like, how am I going to write that? So we're going to count over the 3 that we have, the 1, the 5, and the 0. We're going to keep those. Everything else up to the decimal point gets turned to a 0. So I'm going to get rid of the 26 and I'm going to change those to zeros. Now, if necessary, I would round up, but since that's a 2, oh, it wasn't 26, it was 20. Since that's a 2, I don't need to round up the 0. So it's just going to stay as a 0. I don't write a decimal because that would imply that those zeros were significant. Now, the problem with this particular case is that it looks like I only have 2 sig figs. So the way that I can show that I have a significant 0 here, I can underline it. So that indicates that it is significant. Or I can change it to scientific notation. So if I put it in scientific notation, it's 1.50 times 10 to the 4. So this shows me that I have 3 significant figures. Okay. All right, so I gave you 2 pieces of paper. I want you to look at the one that kind of has a border around it that says calorimetry. What I'm going to do is I'm going to go through a couple of the definitions that are on this page. But if you want to complete it, then you can use that as your extra credit for the last part of the notebook. Okay, so I've given you this piece of paper that has our equation on it. What I want you to do is tape it to the bottom of the page so that you can lift up the equation and see what the different letters are for. So you should have tape at your page to do that. Now, this is the only thing we're going to attach right now. I have a sheet that looks like this, turn it around, that has other things that you can use to cover up things so you can see what they are on the rest of the page. So ultimately, this is going to, if you do this for the extra credit, it is going to end up looking like this. So the top here, where it says calorie or joule, what those are the units of heat. Okay, so we're not doing anything with that right now. So we have two things that look a lot alike under here. You're going to write some stuff. One of them is going to be specific heat capacity, and one of them is going to just be heat capacity. That is beautiful. So let's put specific heat capacity on the left because that's where you're going to put it down below. And so our specific heat capacity is specific because it is per gram. So this is how much energy, how much heat do I have to put into a system, the amount of heat required to raise the temperature, and it has to be of a substance. Okay, so sometimes we approximate the specific heat capacity of other things, but mixtures could have different compositions, and those different compositions could change what the specific heat capacity is. So really, it should be a substance. And we're going to raise that temperature by 1 degree, and we're going to do it per gram. Okay, so if I have twice as much, it'll be twice as much heat, but the specific heat capacity remains the same as we would divide by the mass. When it is the same, regardless of how much I have, this is called an intensive property. All right, so I borrowed this from somebody else, and there was a mistake on it that I did not catch before I messed with it. But if you decide to do this to add the extra things on here, this flap says it does depend on the amount of substance. It does not. So you would need to change that too. It does not change the price. Okay. We are also going to talk about things that just have a heat capacity. So the heat capacity is going to be for an object. So similar definition, it raises the temperature, but not of a substance, of an object. And that object may have different parts that are made up of different things. For example, your calorimeter. So we'll talk about calorimeters today. But it's still going to be how much per degree Celsius. So since it's going to matter what that object is, then it is an extensive property. It is not per gram. I can't just look at one part of the calorimeter. I can't just look at this corner and have it be the same as that corner. It's going to matter where it is, and it's going to matter what it is. Okay, so underneath, we're not going to look at these things a lot right now because we'll get to it in our slideshow. We're going to have some information about specific heat capacity. Inside, we will have the specific heat capacities of different substances. We'll look at that in a minute. We're going to talk about coffee cup calorimeters. And so this is just a picture of them. But what a calorimeter does is it measures the heat. So this is all about heat. It measures the heat absorbed or released by a substance or a reaction. And the key thing to a calorimeter is that we're always measuring the surroundings. So the heat that is entering the system is coming from the surroundings. And vice versa. If the heat is released by the system, then it is absorbed by the surroundings. So the other thing that I did for this is that for the flaps at the bottom, I just cut in between them so I could lift one at a time and see what each of those things are. And then since the equal sign is just equal sign, I just take that down. All right, so if you want to do that for extra credit, there are copies of this part sitting on this table here that you can grab for